Engineers try to solve problems, and a lot of times the solution to the problems that engineers identify involves some kind of a design process, some kind of a design. And engineers have specific processes that they follow so that they can approach problem solving in a systematic way. There are different kinds of engineering design processes. If you look in different engineering textbooks or if you look online, you're going to see a lot of different variations. They all have certain things in common. And one thing they have in common is that they are iterative processes. In other words, an iteration is one time through the process. So in your first iteration, you are probably not going to come up with your best possible design. And so the engineering design process is designed to be a cycle. It is iterative. At any point in the process, you may find that you have to go back and repeat a previous step. Once you go through the entire process, you may realize that you have to go back to the beginning and make modifications to your design, or even start from scratch with a new design. This is one example of an engineering design process. You can see it's broken down into a few major categories: defining and delimiting the problem, designing solutions, optimizing design solutions, and then implementing the solution. And at each point, you are asking questions. We've already we've already started identifying a problem. We've tried to define a problem. Defining the problem involves conducting research on the problem, so you can research other solutions that have been made. You can research specifics about that problem. And then you have to come up with criteria and constraints. It's important to define the criteria and constraints at the beginning of a design process, because throughout the process, you want to make sure that you are adhering to those criteria and you are limiting yourself to the constraints. After you define and delimit the problem, once the problem is well defined, then let me get a pointer here. Once the problem is well defined, then you can start designing your solutions. And you start by brainstorming solutions. In a brainstorm, you just throw out you and your team will throw out as many ideas as you can come up with. You won't even think, oh, that's a good idea, that's a bad idea. Anything is fair play. And then once you have a list of all the solutions you can think of, then you start evaluating those solutions and choose a couple of them, one or two of them, for testing. Eventually, you'll develop and test a model. And once you have a model of a solution that meets the criteria and constraints, then you can move on to the next step, which is to optimize one or more of those solutions, or really one of those solutions. You'll continue to narrow it down until you have the solution that you want. But if your solution does not meet the criteria and constraints, you can reiterate. You can go through the designing solutions step again, or you can even go back to the defining and delimiting the problem step again. This is what makes the process iterative. As you or after you have come up with a design, which might include um, computer models, drawings, written descriptions, then you optimize the design solution and you think about what needs to be, or what should be improved, and you build and test a prototype. A prototype is like a practice design. It's a model, it's a physical model of your solution that you can perform tests on. Okay, so you will um, come up with some kind of, it might be smaller or it might not be fully functional, but it is your first solution, your first attempt to build a solution to the problem, and it's good enough that you can run tests on it, and you can see how well it performs under those tests. And then based on those results, you're going to refine your solution. And once you are confident that this is the best solution that meets the criteria and constraints, some of those constraints may be budget or time, then you will implement the solution, build the actual product, and communicate the results to whoever you're producing this solution for. So let's say you are evaluating materials for bus shelters. You realize that glass is too expensive, but you want to try to figure out what the best or the better alternative material is, wood or metal. What step is this in the engineering design process? Well, if you build and test the prototypes, if you build and test wood and metal shelters and you test them, then that step is build and test a prototype. And then from build and test a prototype, then you go to refine the solution to choose one or the other and consider the trade-offs for wood and for metal. You have some kind of engineering design process that is used to develop or refine technology, not just to invent new products, but to refine products that already exist. So technology is not always inventing something, it can be developing something as well. In areas that whether you're talking about designing a car or designing a pencil, there in either case, engineers will frequently follow similar design processes, even if they're coming up with different products, very different products. So think about why optimization is usually done by making one or a few small stages at a time. Cars have been running on or they've been using internal combustion engines for over 100 years. And we've made little modifications year after year after year with each new model year of a car. So a 2021 car is significantly different than an old Ford Model T. It has a lot of new, but why couldn't car designers jump straight from the Model T to a 2021 Corvette? Well, they had to make little changes all along the way. And now we're even moving beyond internal combustion engines, and we're moving toward the use of electric cars. It is important to define the problem you're trying to solve before you start trying to solve it. And we've talked about criteria and constraints. Let's say a company wants a design for windows in a tall building, like a skyscraper. And it's hard to clean windows on a skyscraper. You've seen videos of window cleaners in places like New York. Well, that's dangerous and it's expensive, and the company would much rather have windows that could be cleaned from the inside. So a cleaner could just somehow open the window and clean the inside and the outside. So what questions would you have to ask to further define this problem? You can't just say, okay, I'm going to design a window that you can clean from the inside and magically there's your design. You have to ask more questions. So some of the questions you might ask are, who's going to use the windows? Are they in homes or are they in businesses? Are you going to have a cleaning crew like in a business, or are you going to expect a homeowner like in an apartment building to clean the windows? Those are different tasks. Should they open just to clean, or should they open for ventilation? Do you need a lot of ventilation in the building? What are some existing designs that address this need? Do your research. See what already exists. You don't have to come up with everything from scratch. Sometimes ideas are patented and you can't just copy them directly, but maybe you would just purchase that other design, or maybe you would modify it some, but over time people come up with solutions that can be used by others. What are the costs, benefits, and risks of each? Remember, costs have to be weighed against, benefits have to be weighed against costs and risks. Will one of these solutions work, or does the client need a new approach to meet new constraints? Is it even possible to come up with a solution for the problem that's presented? While defining their want or need, engineers need to start thinking about the characteristics of the possible solutions. They don't want to get too far into the design process while just defining the problem, but they do start to think about the criteria and the constraints. Okay, criteria are the desirable features of the solution, and constraints are limitations. Maybe you only have a certain amount of time. Maybe you only have a certain amount of money. Maybe it has to be a specific size. So engineers ask questions. They outline the qualities that a solution should have. We call these criteria and constraints. They usually write them down, and they prepare something called a design brief, which might just be like a one-page description of what they're going to design, and lists criteria and constraints, maybe in a numbered list or in bullet points. And they keep this design brief on hand because any solution they come up with needs to stay within the constraints of the problem. So let's say a company is designing a multi-story building and hires you to design the windows. They list the qualities that they are looking for. Now, as the engineer, you're going to have to decide which of these are criteria and which ones are constraints. Windows should fit between the wall supports, which are 125 centimeters apart. Is that a criteria or a constraint? That's a constraint. That's a limitation of the size of the window that you need to design. How about this second one? Windows should be cleanable by one person standing inside without special tools. That's a criterion. Okay, criterion is singular of criteria. Criteria is plural. Windows have to be cleanable. So this is a criterion that they might come up with. I want a window that can be cleanable by one person. And they don't need special tools to do it. They can just use, a rag and a spray bottle or something, or a squeegee. Windows should provide unobstructed views of the outdoors. Which one is that? That is a criterion. That is some feature that the client is going to be looking for in their windows, that you're going to have to design into that. Windows should insulate as well as the walls do in order to keep fuel costs low. What is that? Criterion or constraint? That's a constraint. Okay, that is something that you need to choose your materials, and the way the materials are put together, that limits what you can do. Right? You have to use materials that provide a certain amount of insulation. Window masses up to 10 kilograms per pane can be supported safely by the structure. Criterion or constraint? That is a constraint. Weight, cost, size, these are all examples of constraints. You cannot design a window that weighs more than 10 kilograms. So you have to stay within that constraint. When you start to look at different designs, because in the design process, you're not just going to pick one design and stick with that. You're not always confident that that's going to be the best design. Often you will research and develop multiple designs, or at least consider, let's say that. You will consider multiple designs, And then you have to pick one or two to really develop. And we have a tool called a decision matrix to help design teams pick a specific design. If you think about, well, on a design matrix, you list your design criteria down on the first column, and then I'm sorry, you list your and then you list your possible designs along the first row. So those are your headings. So in this design matrix, we see examples of different types of locks. Okay, in this first column that says weight means you're going to rank the criteria from least important to most important. So aesthetics is the least important criterion here. Safety, very important, because we're talking about locks for windows. Now, the team will get together and they'll assign, let's say they have 3 different locks that they're considering. They will assign scores to each of those criteria. And so lock 1 has a high safety score, but it has a low score for cost, meaning it's expensive, and a low cost for aesthetics. And when you score each criterion on a design matrix, then you can look at the total points and you can decide, well, which one objectively looks like it's the best design to pursue. Now, what the team did here is they took the weight, multiplied it by the score, and then added those products up. So lock 1 was 5 times 4, 20, plus 4 times 2, 28, plus 2 times 1, 30, plus 1 times 1, 31. That's why it got a total score of 31, because safety is so much more important. Safety and reliability are really the important things when looking at a lock. Now, on page 53, you're going to design and record 4 criteria for window designs. One is already put in for you, cleanable from inside. And then you need to weight each criterion. This is something you need to do on your own because everybody's going to have a different answer here. But for each window design, rate each criterion and calculate the total points, and then compare the designs and figure out which one you think is the best choice. Some possible criteria might be the ease of cleaning from the inside. Not just that it's cleanable, but how easy is it to clean? The amount of ventilation, cost, aesthetics, expected lifetime, how complicated it is to order or install, and thermal insulation. Important criteria such as cleaning should be given greater weights. A decision matrix can be useful when there are more than 2 or 3 criteria, or when the criteria are very different from each other. You can use it to examine the trade-offs for different solutions. The total score on the bottom is a helpful guideline, but if you have two designs that are pretty close scores, you shouldn't just go by the total score. It gives you a way to, but it gives the decision matrix gives you a way to narrow down your choices. So let's look at this. Suppose an architect is comparing window designs for the lowest floor of a house. Let's say it's a 1-story house, rather than for a skyscraper. We have different windows for each. Which of these criteria is most likely to be given up in a trade-off? Well, it can't be locked securely. That's really important in a house on the first floor. In fact, that's probably even more important on the first floor than it is on a skyscraper because of security. People don't typically enter skyscrapers through the windows, but that can happen on a house, and you need security. Cleanable from the inside, is that super important? Probably not so much on a house, because if you can reach the windows from the outside. So that's the one that you would probably be most likely to trade off. Ventilation, no, ventilation is important in a house because you need to have air circulate through to be comfortable. Same thing for insulation. you want it to be well insulated. So the most likely trade-off here is cleanable from the inside. Early on in the design phase, an engineer might make simple models to test different aspects of a design. This comes even before prototyping, but then when it is time to prototype, then a more detailed model might be built. It's a full-scale model of the design. Usually works, might not do everything, but it does enough to be tested. So it's your first attempt of really building your solution. Which of these is better determined by using a full-scale prototype of a pivoting window than by using a simplified model? Well, the effectiveness of each of three possible locking mechanisms, that's probably pretty important to have a full-size model or a full-size prototype, because if you just had a little model, it might be hard to produce everything to scale and test it. It's probably even easier to build a full-scale model than a miniaturized version. The weight of different types of glass, that's probably not that important that you have a full-size prototype, because if you build, let's say, a half-size model, well, then you know that if you double the size of it, you're going to double the weight. So you can actually, by knowing the density of your materials and the amount of the materials, you can actually project the weights of different types of glasses from a small model. And how far exactly the window should pivot, you would probably want a full-size model so that you could test that and see it in scale. The best of 20 types of materials for the frame. Again, you probably don't need a full-size model because you can test the properties of materials without building a full-size prototype. There are different ways to evaluate possible solutions, and you can see here, we see that solutions are constantly going through this cycle, this life cycle analysis. If you wanted to caption this visual, you might call it the life cycle of a technology, because there's constantly new science being done, and this is important because it shows the total environmental cost of a solution from beginning to end, because all the materials that things are made of, like an iPhone, I read, the number of different types of materials, it's just enormous, and they all come from different places. So the plastic and the glass and all the different little things that go into the microprocessors and the display, it has a tremendous environmental impact, because all those materials have to be somehow extracted from the earth, processed, stored, and so this life cycle can give us an idea of the total environmental cost of a solution, because each material has its own impact. Solution might sometimes seem undoable, impossible. Maybe some of the designs that you come up with, maybe none of the designs that you come up with meet the criteria and stick to the constraints. And sometimes people continue to develop those because they figure, well, the science will have to catch up, right? The research will have to catch up. We'll design this out of the world thing. So you see this like on super advanced prototypes. Sometimes we put out a design and then wait for the supporting science to catch up to it. But if you can't do that, then any stage of the design process might involve the return to a previous stage, or it might involve redoing that stage. Again, it's an iterative process. It's kind of a funny word. It might be hard to say fast, but learn it. Iterative. The final solution often reflects many refinements of the initial design, because you keep iterating through that process, and then you come up with your best final design that meets the criteria and constraints, and that is what you produce and what you communicate about to your